Hey there, it's Shannon MATHCHICK Myers, and today we'll be looking at series and convergence. So let's warm up first. We spent the last section checking out sequences and ascertaining whether a given sequence, A sub n, converges or diverges as n approaches infinity. Remember, the terms of a sequence are represented as a set or list which need not be ordered. There are finite and infinite sequences. Now, what if we were interested in summing a sequence? So basically adding up all the terms of a sequence. If we're interested in summing up a finite number, say n, of the terms of a sequence, we would be finding the nth partial sum. If we are interested, in finding the sum of an infinite sequence, if it exists, we would be finding an infinite sum called an infinite series or just a series. So a little bit about notation here. If you have, this represents a sequence, and a sequence is a list, which doesn't necessarily have to be ordered, but we'll make it ordered. And then if we wanted to sum up a sequence, we would basically, so this guy is a sequence. Oops, sequence. And then I should probably say A sub n and then comma dot dot dot. And then an infinite sum would be if we went ahead and put I as the subscript, and maybe starting at 1 going to infinity, this would be an infinite sum of A sub I. That would be a 1 plus a 2 plus a 3 plus dot 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 plus a sub n plus dot dot dot, and you keep going. This is a series. You could also call it infinite series. Okay, so our main interest will be to ascertain whether a series converges or diverges. Now, sometimes there is a specific sum that you can find, as you'll see in some of the things we work on today. But if there, just because you find convergence doesn't necessarily mean you find a sum. So that's okay, all right? We're mostly interested in convergence or divergence of a series, and we're interested in certain special sums, infinite sums. All right, so let's check this out. This is a square, okay? So write that in. We have a square where S equals 1 unit, so each side. So then the area of the square would equal to 1 square unit. So another thing to note is, and actually, hang on, I'm going to, instead of writing in little square, I'm going to write this as the area A sub 0 would be 1 square unit. Now, let's take a look at what we have going on, okay? So here we go. If we take a look at this square, so we want to develop, some kind of formula here. That's the evil plan. So if we take a look at our square and we start dividing our square in half, so we could call this first area, area 1, would be, well, each of, if we divide it exactly in half, this length here would be 1/2 of 1, right? So our very first area will be 1/2 to the 1. So the a sub 0 area would be 1/2 to the 0. Let's try this, which, as we saw, was 1 square unit. We're looking to see if we can keep dividing these subsequent areas in half, okay? So now I'll go over here and then divide this part in half. And then we can call this A2. That's going to equal 1/2 squared. I think I'll need a thinner line on my pencil, so I'll go to the pen here. And then if I then go to the next square and divide it in half and call this A3 equals 1/2 cubed. And it's kind of cool, it makes like that kind of snail shape in nature. And then we go to the next square, divide it in half. We have our A4 is 1/2 to the 4th. And then you can keep going, and you'll never quite, oops, doesn't look quite great. You'll never quite find it won't ever end. It will appear to end, but it won't ever quite end. So this one would be A5, which would be 1/2 to the 5th. And then dividing this next one in half, we would have A6, which is 1/2 to the 6th. And then you would just keep on going. I think you can get the pattern here. So this one here would now be A7, 1/2 to the 7th. And then split this up, you'd have A8, etc. And you'd be, continue to move along. So this would just keep going on and on and on. We'd keep, making this smaller and smaller and smaller. Whoops, that didn't work. Okay, that's good enough to show. But you would keep getting this smaller and smaller and smaller and smaller. And it's really, really pretty cool. All right, so let's look at the sequence that we were looking at above. And then for the purposes here, let's take a look at starting with n equals 1, just so that you can see some of the notation without it being a special case. So we're going to write the first 5 terms starting with n equals 1. So we'd have 1/2 to the 1, 1/2 squared, 1/2 cubed, 1/2 to the 4th, and 1/2 to the 5th, which of course is 1/2, 1/4, 1/8, 1/16, and 1/32. Cool, cool? All right, so here's the first 5 terms in a list. Now, sum the first 5 terms. So we're just, instead of commas, we now have addition symbols. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 is equal to, now let's pull out the graphing calculator. You can do a summation on here, which is pretty cool. Okay, so how to do a sum in a calculator. We go to second, catalog. I'm going to go to the T because we're looking for sum, which is near the end of the S's. We pick the sum that has the parenthesis, and then we go back into catalog and go to S because we're looking for sequence, the sequence with the parenthesis in it. Now we need to put what our sequence is, and so we'll put 1 divided by 2. I'm just going to use a dummy variable here, raised to the, I don't know, we could, K is a good one. And then we need to put what our variable is, or with respect to the index of the sequence. And so we chose K. It keeps going to J. And then we're summing from K is 1 to K is 5. And then the change in K is just 1 because we're working with the positive integers here. And look what we get. We get 0.96875. And you can always check it, this is a 7, by summing all the fractions. So you'd have a 0.5 plus 0.25 plus 1/8 plus 1/16 plus 1/32. Enter, and lo and behold, we get our 0.96875. And so, represent this fifth partial sum as a summation. If we go to the summation, and if we put it in terms of n again, we would have, this is actually our fifth partial sum, okay, which would be equal to the summation as n goes from 1 to 5 of 1/2 to the n. Cool, cool? And that was equal to what we got above. All right, now find the limit of the sequence, okay? So the limit as n approaches infinity of our sequence 1/2 to the n is equal to what? Good. As n gets large, the denominator gets super large, which means it goes to 0. So our sequence 1/2 to the n converges. Now let's find an expression for the nth partial sum. So we started with we'll start with S1, and that would just be equal to 1/2 to the 1, right? Now, we want to develop something for, like a pattern going on. Okay, so let's now look at S2, see if we can start developing a pattern. We have 1/2 to the 1 plus 1 squared. Well, let's get one happy denominator. So if we multiplied that first fraction by 2 times 2, we would end up having 2 plus 1 over 2 squared, right? Well, would that work for the first one, right? I mean, that's basically saying we'd have, our proposed Sn would be n plus 1 over 2 to the n. Does that work for the first one? Well, let's try it. That would be 1 plus 1 over 2, which is not true, right? That would end up being 1, not 1/2. So let's think of a different way to write 3 where we're not adding 2 plus 1, okay? So we know that this guy didn't work. So what if we wrote, instead of 2 plus 1 is 3, what if we wrote 2 squared minus 1? Do you agree that that is 3? Cool, cool. It's over 2 squared. So now our next proposed Sn would be 2 to the n minus 1 over 2 to the n. So let's see if that works for the first one. This would be 2 to the 1 minus 1 over 2, which is indeed 1/2. So it looks like we got it going, all right? So the expression for the nth term of the sum, and this sum, so S sub n would be I equals 1 to n, and we would have what we just found here, 2 to the I minus 1. Oh, sorry, and that was a 2 squared. Over 2 to the I. Cool, cool? And we have found this expression. So now, if we come over here and we say, what must be the limit of this expression? Well, we would evaluate the limit, I'll go back to n, as n approaches infinity, of 2 to the n minus 1 over 2 to the n. Now, if I rewrite this as the limit as n approaches infinity of dividing both terms through by 2 to the n, I would get 1 minus 1 over 2 to the n, and that in turn is 1 minus 0, which is 1. Cool, cool? And we are done with our warm-up. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And the next part of the section is coming right up. Bye.